All right, welcome back. It's Thursday. We're doing surface area, and kindly consider the following free response question. 91 BC4 goes like this. It says cap f prime of x is 2 times 2x squared plus 2x. Oh, whoops, I'm ahead of myself. Sorry. I'm looking at the wrong thing. F prime is the question. F is the integral from 1 to 2x of rad t squared plus t. So I gave it away already. What's f prime? That's part A. Cap f prime. Remember the fundamental theorem part 2? Says what? Take this and plug it in where you see t. So what do you get? Rad 2x squared, does this look familiar? Plus 2x, don't forget, we're not just plugging in x, we're plugging in u, so there's a chain rule. So what do you write? 2 times that. Okay, good. All right, let me skip B for the moment. Take a look at C. It says, can you find the limit as x approaches 1/2 of cap f? Okay, yeah? Right, exactly. So let's write that out. So the limit as x approaches 1/2 of cap f is the limit as x approaches 1/2 of the integral from 1 to 2x of, what is it, rad t squared plus t dt. But that's sort of silly, because if you plug in 1/2, what do you get? The integral from 1 to 1 is what? Got to be 0. All right, so that's easy. But what I'm really after is part D, the arc length of this curve. This describes some kind of curve. And do you know what it looks like by any chance? Probably not. This is a very difficult question to graph, right? Okay, so you can ask questions about the derivative. Was it increasing, decreasing? The second derivative you can get. Was it concave, concave down, concave up? Finding some zeros. We just found one, right? That helps you graph it. Okay, well, aside from graphing, what's the arc length? So here we go. Part D. Find the length of the curve along the curve y equals f from 1 to 2. Okay, so again, cap f of x is the integral from 1 to 2x of stuff. Okay, and we want the arc length as x varies from 1 to 2. Okay, so how do we do arc length again? L equals... We did this yesterday. L equals the integral from?
Square. It was square root of.
Yeah, but what are the limits? 1 to 2, right? Okay. Square root of what?
It was
1 plus the derivative squared. But we got the derivative right here. Square this. What do you get? 4. And the radical? Goes away. All right, so let's write that. So 4 times what's in the radical. And 2x all squared is 4x squared, I guess. We could have simplified that before, I suppose. And there you go. That's it. So how do you do this? Can you do this? Is this a U sub? See, with these... Or sometimes you have a perfect square that you can square root. Now it's working. So it's working, isn't it? Yeah, but I can't move. If I move, the wire gets messed up. Okay, so I can talk, but I can't write? Or I can write and I can't talk? Okay. See, it's, all right, whatever. So technically this is an absolute value of 4x plus 1, but 4x plus 1 is positive on the domain from 1 to 2, so it really doesn't matter. So can you anti-differentiate that? What do you get? 2x squared plus x. Alrighty. And we're evaluating that from 1 to 2 using the first fundamental theorem. Oh, we got the second fundamental theorem here, right? We got the first fundamental theorem here. Oh my goodness. All right, so plug in 2, you get 4 times 2 is 8 plus 2, well, that's usually 10. Minus, plug in 1, you get 2 plus 1 is 7 units, whatever they are, feet or inches or something. Okay? All right, so now, what is this stuff about surface area? Well, we're going to talk about surface area of revolutions, just like we did volumes of revolutions with disk, washer, shell. Okay, what if you take an arc, like we just calculated, an arc length? What if you take that piece of curve and you revolve it around an axis of revolution? An x-axis, a y-axis, a vertical line, a horizontal line, whatever. You're going to trace out a surface, not a volume. Can you figure out the area of that surface? Let's see. Let's try this question out for size. Let me try this. All right? Yep. Surface area. Let's try. Ninth period likes this for some reason. No, not that one. Where is it? This one. There you go. Yeah, for some reason, ninth period likes this for axes. Huh? Is it Candace? No, I think it was Rachel, actually. But, all right. So let's say there's your x, there's your y, and there's your origin. Consider the curve that goes through a y-intercept of 1 and goes down asymptotically to the x-axis. It never touches. Okay? Can you figure out that arc length? Now, you might think that it's infinitely long, right? So that length doesn't exist?
No, it does.
Okay, what if I revolve it around the x-axis? Is the volume finite? Is the surface area finite? I don't know. Let's find out. Let's answer these questions. This is called Gabriel's horn. Named after my son. No, not really. Named after Archangel Gabriel. He's got one massively long horn. Why? Because he's got to call the whole host of angels to go to war during the last days, right? Have you heard about this stuff? So he's got this big-ass horn, okay? It's based on y equals e to the negative x. That's what this is. Exponential decay. All right, so you take this thing and you revolve it around the x-axis and you got your horn. It's made out of brass. My question is, how much brass is that? Okay? What's the surface area? How much brass do you need to make this horn? Well, we can answer 3 questions. What's the arc length? What's the volume of revolution? And what's the surface area? Let's go straight to arc length, okay? So the arc length is the integral from what? 0 to infinity. I'm starting at x equals 0, going on forever. All right, this is what's known as an improper integral. You can only do this with a convergence table. Plug in bigger and bigger numbers. Remember the last test where I had you find the area under e to the negative x squared from negative 1 to 1, from negative 10 to 10, from negative 100 to 100? That table you filled in? That's a convergence table trying to figure out an improper integral. You were doing it already without knowing it. All right, so we have to do some kind of a limiting process here. Now, what are we integrating? The square root of 1 plus this thing's derivative squared. Well, if y is e to the negative x, what's dy dx? Negative e to the negative x. Remember, we know the derivative of e to the u is e to the u, du, negative 1. All right, isn't that negative 1 over e to the x, by the way? All righty, so what's that squared? What's dy dx squared? Well, do I have to write it? What's this thing squared? Square it. Negative 1 times negative 1 is? Positive 1. E to the x times e to the x is? E to the 2x. Okay, that's what I'm integrating. All righty? Now, is there any way that could be u subbed or something? Or is it a perfect square? I don't know about that. Maybe, I don't think so. You could maybe rewrite it, but sometimes this helps. If you rewrite it this way, whoops, 0 to infinity. With a common denominator, multiply top and bottom by what? E to the 2x. So really what you have is e to the 2x plus 1 over e to the 2x. And then you can take out the e to the 2x outside as 1 over e to the x. Does that help? No, it doesn't, does it? That's a shame, because, see, it would have helped if this had to do something with, like, e to the negative x, right? Because the derivative of it would have something to do with e to the negative x. So it would be a u sub, but the negative went away because we squared. Right? Yeah. Or not. Negative went away when we combined the fractions, right? So, yeah, it's still not a u sub, and it's not a perfect square. Can you factor that as a perfect square? Nah. All right, so I'm not going to do it that way. Forget that. What am I going to do? I'm going to do a convergence table using Hal, right? All right, Hal, get to work. Here we go. All right, so what I'm going to do is I'm going to put in different values of b into this definite integral from 0 to b under the square root of 1 plus 1 over e to the 2x dx. All right, so we're just going to plug in a bunch of values. Let's say 1, 10, 100, 1,000, and see if it starts to converge or not. Right? Okay, let's ask Hal. Okay, Hal, do stuff. All right, so here's Hal. So I'm going to do a second 7 of, let me put it over here, of the square root, wake up, no, I don't want you, square root of 1 plus 1 over e to the, which is diamond this, 2x. Okay, now close the square root, and we close the exponential, right? We close the square root, and then comma, x. I'm just curious, is there an antiderivative of this thing? It involves ln, we don't know that one yet. And stuff. Yeah, that's a beast, I'm not going to do that. Okay, and then I want to go from 0 to 1. See what I get. Now it's going to give me an exact answer because apparently there is an antiderivative. But I don't want that. I'm going to diamond into that. I want a decimal. Alrighty, so there's my estimate. Now if I want to do like a fixed 4, let's do a fixed 4 in our heads, right? It's 1927. I want the answer to 3 places, so if it has round-off area in the 4th place, it's okay. So 1.1927. Okay. 1.1927. Okay, what happens if we plug in 10? Where's Hal? So let's plug in 10. And diamond enter. So I don't, or I could change it to approx mode, whatever. And working. And I got 10.2260 if you're rounding up to 4 places. 10.2260. Is this getting closer and closer to something? I don't know. It's not looking very hopeful. All right, let's try 100. Go away. You know, smartboard, you're pretty dumb for being a smartboard. Okay, let's go and put in a 0 and see. Oh, it's going to give me exact answer. I didn't do diamond, damn it. Diamond, enter. And okay, Hal, do I need a ludicrous speed? Come on. Just a definite integral. 100.2260. Are you getting a pattern here? 100.2260. What do you think the next one's going to be? 1,000 point stuff, probably 2260. Yeah, so I can make this arbitrarily large. It's not getting closer and closer to anything. This limit does not exist, therefore this arc length does not exist. Okay, that's okay. Doesn't exist, the limit doesn't exist. All right, but wait, what about the surface area? Let's try surface area. Now, how the heck are we going to do a surface area? Let's take a look at this graph again. So let's say we took a piece of arc and we revolved it around the y-axis. We're trying to get the area of that surface, not the volume, the outside surface. How much brass, remember? Well, we have this length. I want to get I want to get a two-dimensional value, right? An area. So I got to have a length times a width, or a base times a height type of thing. What if I take the arc length and multiply it by the circumference of rotation? If you unravel that, don't you get sort of like the Coke can is a rectangle when you unravel the Coke can? Same idea. Not exactly, but since we're making it very, very small pieces of arc length and adding them all up, it pretty much is. Okay? So the surface area is going to be the integral from 0 to infinity of 2 pi r dl. Maybe I'll take the 2 pi out, just for fun. 2 pi, the integral from 0 to infinity, times the radius of rotation times the L. What's this? This is the arc length stuff we did. We already figured that out, right? What's R? What's the radius of rotation? Isn't that the y value? Right? That's the radius of rotation? Sort of like when we did shells, 2 pi r, right, circumference of rotation times the height times the thickness. Well, now it's not three-dimensional. I only need that length. All right, so r is going to be e to the negative x. And dl is going to be what we wrote before. Look, here's dl right here. What we integrated before. This is dl. Okay, so let's write that. That's a piece of arc length. So it's radical. Oh, whoops. I guess I'm red now for some reason. Radical 1 plus, well, e to the negative 2x, wasn't it? It was 1 over e to the 2x. I'm writing it this way on purpose because I'm thinking it might be a u sub now. That's convenient. It's to the 1/2, right? Let's see. Ah, interesting. Well, who's u? If this is a u sub, who do you think u should be? The inner function is 1 plus e to the negative 2x. What's du now? The derivative of 1 is 0. Derivative of e to the u? E to the u times negative 2. Don't forget the dx. Well, that's not quite right, because I don't have an e to the 2x, do I? So it's not a u sub, is it? If I had an e to the 2x out here, I'd be in business. Yeah. E to the negative 2x. I have e to the negative x, but not e to the negative 2x. So no, can't do it. Too complicated. If I replace what do I replace dx with? I replace dx with du over negative 2 e to the negative 2, e to the 2x. Doesn't match. Too much information. Can't cancel all the x stuff out, right? So guess what? We're going to do another convergence table. Here we go. Okay, we're going to ask Hal to do some work. Wake up, Hal. Let's see. Yeah. All right, so let's draw a little table. Not you. Where did it go? You. Okay. So I'm going to plug in bigger and bigger values of b. I'm thinking area is the integral from a to b, right? B is getting bigger, bigger, and bigger. From the integral from 0 to b of e to the negative x square root of 1 plus 1 over e to the 2x dx. Which is the same as before, so now I have that e to the negative x here. That's what's different. Now this number gets smaller, really smaller and smaller and smaller, really, really, really fast, right? So just because the arc length didn't converge doesn't mean that the surface area doesn't converge. Who knows? Let's plug in different numbers, different values of b as they get bigger and bigger, closer and closer to infinity. I don't know how much I'm going to need. All right, and we're going to plug this into Hal. Okay, well, Hal already has all of this, except for the e to the negative x. So let's doctor this up a little bit. There's an e to the negative x in front of the radical, right? So let's put that in there. Diamond this, negative x, close it. And let's go from 0 to 1. I had 1,000 or something? No, 100. Okay, so ding, ding. And diamond that, diamond enter that. Okay, let's see what we get. 0.77, for 4 places, 0.7718. Hello, 0.7718. Okay, let's do 10. Stop it. Okay, I gotta get rid of this smartboard software. It's driving me nuts. Okay, now we get what? 1.1, you said? 1.1477, okay. 1.1477. It's not blowing up as quick as before, right? So maybe this is converging to something. Let's try it again. Do the 100. I know, stop it. Stop it. Okay. It's close already? Really close?
Yeah, it's
1.14. All right, I'll take your word for it then. So 1.1478, and hopefully it stays that way. We're done, right? Well, did mine even finish? It did 10. It didn't do 100 yet. Do I need ludicrous speed? Holy cow. Yeah, if you run this off the 4 places, it's 7, 8. All right, so do 1,000. I should go to do ludicrous speed, I suppose. Did anyone get it yet? Is it the same? 7, 8? Okay. So let's just do 7, 8. All right, so that converged. I don't know the exact answer. I don't know this in terms of E or pi or something or radicals, whatever, but that's a good enough answer. I'm going to say that the surface area, therefore, is approximately 1.147. Remember, the 8 might have round off error, so I don't trust it. And so, so Gabriel's horn is infinitely long. The arc length doesn't exist, but you can build it. It's only 1.147 square feet of brass if the units are in feet that we started off with, right? Does that make a lot of sense? Not a hell of a lot of sense. But 'tis the nature of improper integrals. Okay, try that again. Let's change Gabriel's horn's shape. What if it's based on a different function? Let's say 1 over x squared, the hyperbola. It doesn't hit the y-axis, doesn't hit the x-axis, right? Y equals 1 over x squared. And let's say I go from 1 to infinity. I can't go from 0 to infinity because it doesn't touch the axis. Okay? Well, maybe, but let's not do that right now. Okay, so can we do this arc length? Can we do this surface area? All right, let's see. If y is e to the negative 2, what's dy dx? Negative 2 x to the what? Negative 3. And isn't that just negative 2 over x cubed? So what's dy dx squared? Don't I need that for the arc length? What is it then? 4 over x to the 6. Okay, so let's set up the arc length. The arc length is going to be the integral from 1 to infinity of the square root of 1 plus 4 over x cubed. Okay? Alrighty. I'd say again? Oh, is it? Oh, wait, look. It's 4, oh yeah, to the 6, wait, oops. And I don't think this is factorable in such a way that you get a U sub out of this. I don't think this is factorable in such a way that you have a perfect square. So guess what? You do convergence tables here. But that's not my question right yet. My question is, how do you convert this to a surface area problem? If I take this arc and revolve it around the x-axis, say.
Well, we need to add
2 pi r. And who's r? Ethan?
r would just be 1 over x squared.
1 over x squared. Okay. So let's convert it. The integral from 1 to infinity of 2 pi 1 over x squared rad 1 plus 4 over x to the 6th. Okay, dx. By the way, while we're at it, could you make that a volume of revolution? If you had vertical strips in thickness dx, is that disk, washer, or shell? Disk, right? So it's pi r squared. Who's r? Y. So if you square y, I want r squared. This is r, so square it. 1 over x to the fourth. So I'm going to write this from my volume of revolution about the x-axis. Let's see if I can sneak all of these in one line here. Pi, the integral from 1 to infinity, of r squared times the thickness. That would be 1 over x to the fourth dx. I don't think there's a u sub either, so you'd have to do a table, convergence table, to find the limit as b gets bigger and bigger and bigger. You'd have to do a table here, right? This one you could probably do, at least the antiderivative. Why don't we finish the volume? What's the volume of Gabriel's horn if that's the shape? Well, the antiderivative is what? This is really x to the negative 4, right? So how do you do that? Let's do this one, the volume. It's x to the negative 3 over negative 3. So it's negative 1 over 3x cubed. Is that the same thing? Okay. And now, well, you know what? Let me be careful with this. Can I find this limit? Let's see. It's pi times the limit as b goes to infinity, going from 1 to b. All right, let's see if we can work this out. It's pi times the limit, or you can put the limit, you can put pi in there if you want, doesn't matter, of negative 1 over 3b cubed minus a negative 1 is plus 1 over 3 times 1 squared is 3. Does that limit exist? As b gets humongous, what does 1 over b cubed do? It gets really, really damn small, in fact, insignificant. So what's your answer? Pi thirds. Okay, so Gabriel can blow the horn because it has a finite volume. It has a volume of pi thirds cubic feet. Isn't that nice? How do I get that? Well, as b gets bigger and bigger and bigger, like 1, 10, 100, 1,000, a million, 1 over b cubed gets bigger still. 1 over 10 cubed is 1,000. 1 over 100 cubed is, what the hell is it, 10 million? No, 1 million. And 1 over 1,000 cubed is a trillion, and so forth. So this gets as small as you want. It basically goes to 0. This goes to 0 in the limit, so you get 1/3 of pi is all that's left. Yeah. That's what we did. Whoops, not here. That's what we were doing here. That's a limit as b goes bigger and bigger and bigger. That's what we were doing. This is a limit, right? This one we couldn't do algebraically, so we did a table. We're trying to figure out, as we go from 0, in this case 1 to infinity, we're going to figure out the length, the arc length, the surface area, and so forth, right? So that's a limiting process. I can't do that any other way. Okay, and you know what? I better store this. What am I doing? I got to store